Okay, welcome to today's lecture. We're starting a new chapter on radical and rational functions. So we're going to start with reviewing a little direct variation, but you can see here our today's learning goal. Inverse, joint, and combined variations are also going to be discussed. The process about finding the constant variation, things like that, and how we're going to use these problems in real-world situations. So, to start with, review direct variation. Remember, it was the equation y equals kx to the n, where k could not be 0, because that would wipe everything out, and n had to be greater than 0, and most of ours were nice whole number exponents. We would read this equation as y varies directly as x to the n, or y is directly proportional to x to the n. Now, one other thing, probably can't read that real well. K is never mentioned, you'll notice, when we read that over there. We never said anything about K. K is never mentioned in the reading of the equation. K was called the constant of the variation. So you need the constant in order to be able to work any other values of the variation. And I think you'll remember some of that process, but we'll be going over it here real quick, like right here. So if I said, starting over, y varies directly as x, write an equation that relates x and y, then find the value of y when x is negative 2. Y varies directly as x, immediately your thought is, all right, we've got two values, 2 and 8, but before we do that, let's just start with the generic equation. Y equals k, x to the n. You know this form because it's said directly. And now the other thing is, you know that your exponent is a 1 because it didn't say y varies directly as x squared, or as the square of x, or the cube of x, or any of those. So you can even detail it a little more. And so now when we put our values in, which we're given, x is 2, y is 8, we can get a new equation where all we have missing is k. 8 equals k times 2 to the first. We would then divide both sides by that 2. When we do, we get a k value. That k value is the constant of the variation, which means we can go back and write the equation with just that k value in. And our new equation we can use for any situation, scenario, dealing with this problem would be y equals 4x. So if I now said, as the third sentence says, find the value of y when x is negative 2, I can just substitute, do the math in my head or not, and know that y is negative 8. Same thing, if I would say, find the value of y when x is 5, you're going to do 4 times 5 equals y equals 20. And so you would be good to finish that way. Now, you should remember the direct variation, hopefully, because now we're going to throw a few others at you. Look at this one. It looks very similar in terms of the slide as well as the setups. Y equals k divided by x to the n, where k again is non-zero and n is greater than 0. And again, we're going to be mostly dealing with positive exponents. This time, though, you'll notice instead of a multiplication look, we have a division look. So it's read as y varies inversely as x to the n, or y is inversely proportional to x to the n. Now, when we go through the process again, that k value is not talked about. It's never mentioned. It is the constant. It is a value you have to figure and work out as you do the problems. So, here is an example. A real-life, real-world situation. The intensity I of a light reaching you from a light bulb varies inversely with the square of your distance d from the bulb. When you are standing 10 feet away from the light bulb, its intensity is 130 units. What is the intensity of the bulb when you're standing only 4 feet away? So let's start with what we did in that last problem, and that was write your variation equation from that given information. So the intensity I of a light reaching you from a light bulb varies, so equals inversely. You know you have a division look immediately with the square of your distance d. You also know that your constant has to be up top, and it said with the square of your distance d, not with your distance d. So you have to put your exponent there. So there's our generic equation. We weren't given k, we weren't given anything till the next sentence. Now here we go. When you're standing 10 feet away, which we know is our distance, so let's start filling in what we know. If we know our distance is 10, but that's still squared, so we got to put the squared next to it. From a light bulb, its intensity is 130 units. So we know the intensity is 130. We still know nothing about K. But since 10 squared is 100, and that's a division, to undo that, you'd be multiplying both sides by 100. So if we multiply this by 100, and we multiply this by 100, that means just take that 130 and move it 2 places to the right, and we'd be looking at 13,000 for K. If K is 13,000, we now have a new equation that we can use for whatever setup it deemed necessary for the situation, which has to mirror what we started with. So now, what is the intensity of the bulb when you're standing only 4 feet away? So we would erase our, got the whole thing erased there, we would erase our D, put in a 4, and go back and square that. So our final math calculation would be that 13,000 divided by 16. So 13,000 divided by 16. And so our final answer, our intensity, would be about 812.5. And that would have to be the intensity, and the intensity was just in units. Okay, and it makes sense because, look back at your original. When we were 10 feet away, the intensity was 130. We got closer and we were 4 feet, the intensity is greater. So the closer you were to the light source, the greater the intensity. The farther you were, the less it was. And that made sense with our situation here. All right? So 10 feet away, we were 130 units. 4 feet away, we were at 812. Much more intense. Now, there's 2 other types, something called combined and something called joint variation. So let's talk about them separately here. Combined is exactly what the name says. When you take anything that's direct and inverse and put them together, then we will have what's called a combined variation. You could have one direct variable, a different variable inversely in the same sentence, and we can get a new variation statement. Can have 2 or more variables. So you could actually have 3, 4. Doesn't stop right there. We could have several things going on. It just depends how many variables are in the situation that's being discussed. So combined, fairly easy name, at least one of each type. Versus the other type here, joint variation. And I think this word joint goes back to like plumber's joints, where you have a joint fitting and your joint of an arm. They have to work together. But one quantity varies directly as the product of 2 or more variables. So this is all direct, no inverse at all, so there's no division look. So a typical equation, I'm just making up variables, might be y equals, k is our constant. We might have a, b squared, c cubed. We might have something like that. Everything has to be multiplied, right? Every variable that's included has to be a multiplication. Again, these allow for a little more complicated scenarios, more than one variable in the independent slot. Independent, dependent, remembering those variable names from before. So here we go, another real life situation. A baseball pitcher earned run average varies directly as the number of earned runs allowed and inversely as the number of innings pitched. Write a general equation to model this situation. So let's go, we'll use the little purple box here. Baseball pitcher's earned run average. I'm going to call that as E, because you can't put ERA, it'll look like 3 variables. Varies equals directly, so we know we got to have our K value, and it's all multiplication now, as the number of earned runs allowed. So I'm going to say we got two numbers here. Number of earned runs, so let's go R for runs. And inversely as the number of innings pitched. Instead of an I, because it looks too much like a 1, I'm just going to put a P. All right. Whoops, sorry, it did say inversely. Directly as the number of earned runs, and inversely, so I do need a division. So this is an example of combined variation. And inversely as the number of innings pitched. So there's my P down there now. Write a general equation to model the situation. There it is. That's as pretty general as we can get. Okay? So now, in a recent year, a pitcher had an ERA of 2.56. So we know where that goes. 2.56 is our ERA. Having given up 72 earned runs. So 72. And that was in 253 innings pitched. So 253. So right there's our situation. To undo this, obviously, the quickest way with both those numbers there would be the reciprocal. So 253 divided by 72 is your thinking. That's going to come over here. 253 divided by 72. And again, we can do this math. This side's going to cancel totally. And let's see what we get with our handy-dandy calculator. All right, 253 times 2.56. That equals, and now we'll divide that by 72. And so we're getting 8.995-ish. So K equals 8.995-ish. There's going to be some rounding directions usually. So if K, that's our constant, how many earned runs would the pitcher have given up if he had pitched 300 innings, assuming that his ERA remained the same? Now let's just back this up a hair. Just need a little space, and we're going to go down here too. So knowing that we have what we have, we would need to start over again. How many earned runs would the pitcher have given up if he pitched 300 innings, assuming the ERA remained the same? So we should be looking at a 2.56 still for our ERA, equals, our K value is at 8.995-ish number now. And how many earned runs? We don't know if he had pitched 300. So here we go. Do the reciprocal again for our math, and we should get our R value. So let's see what happens. Pull that calculator back up. Right, if we use the reciprocal, we're going to have 8.995. I did write it down correctly. If we pull that back up, we're going to have that 2.56 times by, the reciprocal would mean the 300s on top, and then we'll divide by that 8.995. So we're getting about, how many earned runs would the pitcher have given up? He would have had about 85, what did it say, 85.3, pull that back up again, 85.3 earned runs. Okay, so we can do that with situations where it's both directly and inversely. Now, lastly, this is more of a reminder. When you hit page 44, there's an example about gears and the teeth in the gears, etc. If you get an equation that looks like this, we have 1, 2, 3, 4 variables going on. But if I would solve for any of those variables, you can see how this equation would be then a combined. Because if I just solve for T sub A, then I know I'm going to have little t sub B, S sub B, they're not going anywhere, but then the S sub A would have been over here, and you can see we have some multiplication and one division. So that would be a good example of a combined situation. The only thing I'm going to caution you on, when you get some of these, make sure you do, well, check to see if you have to do any converting on the units, inches, feet, miles, etc. because they like to sometimes throw that in and you forget totally about that. So double check on some of the word problems. Make sure you have consistent units would be a good way to say it. So more variations. We now really have 4 types: direct, inverse, combined, and joint. And you should have a good grasp on how they're all going to work and in relationship to real world problems you'll find them in. Bring any questions you might have back with you to class.